What is up, ladies and gentlemen? Today is the 25th of December for those of us who are in Singapore. First of all, let me wish you a Merry Christmas and Happy Holidays. Unfortunately, we are not going to be nearly as merry over here, so we are simply going to sit in this corner over here and talk about some math. Right, today's video, I'm afraid to say, will probably be slightly longer than usual. This is a big topic and I will probably not rush through it nearly as much. For those of you who are busy around this point in time when you are watching it, you might want to split this into two different sessions actually. Okay, so without any further ado, let us begin. Right, so today what we'll be talking about is I want to revise our concept of indices, in other words, exponents on algebra. Then afterwards we will talk about exponential functions, graphs and math problems. And then we will move on to talk about, informally, the opposite of exponentiation, which is using logarithms. We will also see algebra problems involving logarithms, as well as, of course, the graphs of both exponential and logarithmic functions. Alright, now without wasting any more time, let us get started. So first of all, right, I want to just briefly remind all of us here of the various laws of logarithms that we have already learned. So most of these should already be familiar to you. In particular, it's important to recall that we would have already seen such a thing in our E-math, right? So actually what we see in A-math is going to simply be more of the same thing again. In that sense, there's really not much to be worried about, right? Do take note, however, that some of the more, shall we say, obscure or more difficult properties will be more common in A-math. So for example, this informally, it looks like a factorizing of the power, as well as fractional indices. We will be seeing formulations with these expressions a lot more often in our A-math problems. Right, so aside from that, the next thing we need to recall is how exponential functions work. So for exponential functions, we will say that the function f will be equal to any number to the power of x. Any number in this case is not absolute. We cannot have 0, we cannot have 1, because 0 to the power of anything remains as 0, 1 to the power of anything remains as 1. So as long as we don't have those two forbidden numbers, we will call this an exponential function, and then we can see all kinds of formulations like so. The number below will be the base of the exponential term, whereas the number above x is the power, aka the exponent. We can also call it index, but it sounds a little bit weird because the plural form is indices and most people will be confused by that. Over here, I will typically swap between exponent and power. Right? So for exponential functions, the key thing to understand about how they work is we need to first recognize what the word exponential by itself implies. So in this case, we need to know that exponential is always a drama queen, right? It's always compounding onto itself. If I am increasing, my speed itself will be increasing. If I am decreasing, my downfall itself, right, the speed at which everything goes worse, will be decreasing. So increasing at an increasing rate, decreasing at a decreasing rate. If we attempt to draw it out, we should roughly see something like so. I can be increasing slowly, increasing quickly, increasing dramatically. This will be exponential. Alternatively, I can be decreasing rapidly, decreasing mediocrely, decreasing slightly. This will also be exponential, right? So as long as we have an exponential function, we can expect to see these kinds of trends. And this will be instrumental when we draw the graphs in a while from now. Right? So aside from all this, one other thing to take note is that we typically don't use negative numbers, right? You won't expect to see, for example, negative 2 to the power of x, because this brings a whole slew of problems, right? If you have an odd number x, it will be negative, but if you have an even number x, it will be positive, and then it will alternate, which will be very painful to deal with, and also not nearly as common when we look at applications of the math you learn in school in real life, right? So even in the A math syllabus, we will not be focusing too much on all of this stuff. Right, so for the next section, we will be talking about exponential graphs. Now, one thing about the graphs is, aside from the trend of increasing at an increasing rate and decreasing at a decreasing rate, we must also note one crucial detail, which is that any exponential, right, where the base, small letter a, is non-negative, right? Well, in fact, rather if it's positive, because if it's 0, it would just be 0. But for anything where the base is 0, we can expect that the exponential term, a to the power of x, is always going to be positive. Of course, this assumes that we are working with real numbers in the first place, right? Because our syllabus is restricted to real numbers. So in this scenario, then what we will see is that because every single output is positive, I will always be above the x-axis. In other words, we can expect the graph to be floating, right? So that is one key detail that we will need to work with. So aside from all of that, we can also see that just like all the other graphs we have learned so far, there might be minus signs all over the place. So if there is a minus sign on the power, in other words, a to the power of negative x, the graph will change from the one on the left to the one on the right. In other words, we will see increasing at an increasing rate to decreasing at a decreasing rate. Right, so the curvature should be reasonably apparent. We will see something along the lines of, let me see now. Where is my cursor? My computer does not want to cooperate with me today. Okay, there we go. So in the diagram on the left, as we indicated, we will increase slowly, increase quickly, increase very quickly. The increase itself is going faster. The increase itself is increasing. So when I have a negative on the exponent, then instead what we will see is I will decrease quickly, decrease at an average pace, decrease slowly. The decrease itself is decreasing. On the other hand, if there is a negative on the outside, not on the base, but just on the entire outside like this, then we will simply flip the graph like that, right? Similar to how x squared was a U shape, but negative x squared was a flipped N shape. It is the same thing over here. If there is a negative attacking the entire exponent term, we will simply flip vertically. One small caveat for us to be aware of is what happens when we have different bases on the same diagram. So the one with the larger base will simply be more dramatic. They will overreact more, and we will see that it is more steep. It will be higher in the positive side. It will be lower on the negative side. So in this case, you see that the black graph will be more extreme than the blue graph. The blue graph is flatter. I will give you a moment to read this by yourself. This isn't looking good. My mouse seems to be a little inconsistent today. Well, it's fine. We will have to work with this. Right, so over here, if we instead have negative indices, so for example 2 power minus x, 3 power minus x, then 2 power minus x will be flatter, right, like so, whereas 3 power minus x, we can expect him to be more dramatic since he is the one with the larger base. So on the positive side, which is the left, he is bigger. On the negative, or rather on the negative x input side, where the indices are positive. That is such a mouthful. On the positive indices side, then we can expect 3 power x to be bigger, and on the negative indices side, we can expect 3 power x to be smaller, right? So over here, the positive indices side will be this region and this region, right? So over here we have a positive exponent. Okay, so over here we have a few drawing practices to work with. In this particular portion, I will only go through a few exercises because I don't want to draw everything while my mouse is not fixed. My current plan, in order to account for the, shall we say, technical difficulties, is for us to simply cover the content, and then I will put the worked practices in a separate video. I think that will also be useful for the viewers in order to separate it, right? So that you don't have to digest everything at once. So for now, I'll simply work with a mouse because my stylus doesn't want to work. In this case, let's start with the first few examples. I will go through some of them. The first one, e power x. E is equal to the exponential constant, right? Euler's constant 2.718. So in this case, it will be a positive number. X itself has no minus sign, so it will be the classic exponential. Remember to label the y-intercept. In this case, we know the y-intercept is 1 because you can find the y-intercept simply by substituting x equals to 0. And when you have x equals to 0, what we will see is that you have e to the power of 0. Anything to the power of 0, as long as the number below isn't 0, will give you 1. And that's why the y-intercept is at 1. Right, so let's take a look at exercise C as well. Exercise C is 3 to the power of negative x. We actually already saw this just now. This will be the classic decreasing exponential. Now exercise D is a lot more interesting. It's negative 5 to the power of positive x. Now 5 to the power of positive x, right, it's going to be like this. It's a positive exponential. But there's a negative sign attacking the whole thing. So we're going to have to flip the entire graph, which will normally be floating above like this. We're going to have to flip the whole thing downwards like that, right? In other words, we will only draw the one below. So let me get rid of the guiding dotted lines, and we shall plug in the graph as follows, like so. And then over here, instead of positive 1, it gets flipped to become negative 1. Alright. Now exercise E is also very interesting. We have over here 3 bracket 5 to the power of x and then 3 5 to the power of x on the denominator. So we could actually simplify the second one into 3 5 to the power of negative x. Negative x. In other words, the first graph will be 3 5 positive x. The second graph will be 3 5 negative x. In other words, in the graph, we can expect to see one person, the first one, to be the standard example of increasing, and the second one will be a standard example of decreasing. So they will be symmetrical. Do take note that because of the 3 in front, when you substitute in x equals to 0, this y-intercept here will actually give you 3, not 1. So be careful of that. And since this graph, or rather this problem, has 2 different graphs, you know for a fact that you're going to have to label both of them. Right? So these are just a few examples for now. Let us move on, and I will probably cover more examples in the second video once I get the stylus fixed. So the next section is a short one. We need to understand how to do equations when indices are in Venn. Fortunately, the usual strategies will work. We can simply compare coefficients or compare bases, the number below, or compare exponents, the number on top. Right, so there are some worked examples given over here. They are pretty straightforward, so I would not like to waste too much time over here. Okay? There can also be problems where we use exponents in order to talk about real life quantities that are increasing or decreasing. So these questions are typically quite straightforward. They will simply require you to read the question in context. So for example, over here, if you look at question 1, part 1, they would like you to find the initial number of sheep. So the key trick to understand is that initial simply means that we substitute in time equals to 0, because initial means at the start. In other words, time has not started flowing yet. So we will substitute in time equals to 0. Right? Now, similarly, another common trait is that instead of asking you to substitute in numbers, we sometimes see that they will tell you the numbers in context instead. So for example, in this case, they ask for 105 days. The question makes the assumption that 1 month is 30 days. So if we have 30 days, you will take 105 divided by 30, which will give you 3.5. And therefore, we will substitute in t equals to 3.5, not t equals to 105. Right? And of course, some questions will ask you for some common sense questions, such as what happens when the time goes to infinity, in which case we will look at the graph itself, because the graph eventually flattens out towards a certain number. And then for part 4, they'll ask you to draw the graph. This is quite straightforward. Right, so I will want to talk more about this flattening out. Earlier on, when we saw the graphs, most of them have been floating on, or rather floating above the x-axis. In reality, this is not always true. If I have a graph where I have an extra constant added or subtracted, this will be a very different story. For example, let's say this is e to the power of x. What if I have the graph of e to the power of x? The entire thing externally we will plus 1. Now we recognize the plus 1 on the constant as everything in the graph moving upwards by 1 unit, so we can expect it to be floating higher. But when everything moves up, that means that number 1, the y-intercept moves up. Number 2, instead of floating above the x-axis where the height is 0, this forbidden height where I float above will also increase. So we have an asymptote, a line that we can grow closer to but can never touch. And in this case, the asymptote will be at y equals to 1. the horizontal line. It's equal to 1 because we started from 0, which is the x-axis, and then we plus 1 upwards. Right, we will be talking about these asymptotes a little more later as well. Okay, let me take a water break. Okay, I am back and my stylus is now working actually. So in that case, let us return to the graph drawing section and we shall talk more about what we just discussed. The concept of having all these, shall we say, asymptotes. Right, so let's take a look at some of the more complicated examples. We will start off with exercise F over here on the bottom left. So exercise F, let me move the screen. Exercise F here gives us 6x plus 2. Right, so in this case, we know that 6x will typically just be your usual exponential. However, we have to move up by 2 units. The forbidden line, which was originally on the x-axis, will also have to move up by 2 units. Therefore, we can start with a forbidden line over here, y equals to 2, and then we can draw the exponential, y equals to 6 to the power of x, entire thing plus 2. Y-intercept over here, as usual, you will substitute in x equals to 0, you will get 3. Now part G is even more entertaining. Over here, we have instead minus 3 minus 5 to the power of 2x. So in this case, what we will observe is that minus 5 to the power of 2x, right, will be similar to an earlier example. The negative is attacking the entire exponential term. So we can expect to flip downwards like this. Afterwards, what we see is that there is a minus 3. So we should expect to move down by 3 units. This includes the forbidden line, which starts from 0. Therefore, the final result will be something along these lines. Not drawn to scale, obviously. right? So we will have the following. In this case, the negative 4, this y-intercept will, as usual, be obtained from substituting x equals to 0. So the next problem will be even more entertaining. This time around, we see that y isn't even the subject. So we will have to do the rearranging by ourselves. And in this case, you will notice that we can actually start by doing this, which then converts into negative indices. That's an x at the corner. From here, then we can move over the negative one, like this. So we have negative indices, but at least we have a plus 1 on top. As a result, in this case, we really don't need to panic that much. Once the rearrangement has been done, we essentially have more of the same tricks as always, right? So in this case, there's a negative on the indices. We expect ourselves to be going downwards. There's also a plus 1 externally. So if there's an external plus 1, we can expect to be floating above the asymptote y equals to 1. So from here, we will be decreasing normally. So let us draw the exponential, label the y-intercept, label the graph. Whether you want to use the modified name like this, or if you would like to use the original name of the math problem, for example, like that, regardless of which one you choose, if you remember, it does not matter. All we want to see is that you actually know the name of the person you're drawing. Right? So I think that will be enough examples for now. One last thing I would like to bring up, however, is, which is not really covered over here, is that once in a blue moon, you will get a base that is very small, in between 0 and 1, for example. So if you have a situation like that, the rules will actually be a little bit weirder. Let's say I give you, for example, y equals to 3 over 10 whole thing to the power of x. What we can do is we can change this to 1 over 10 over 3, the entire thing to the power of x. This changes to 1 power x, 10 over 3 to the power of x. This changes to 1 over 10 over 3 to the power of x. This changes to 10 over 3 to the power of negative x. Once we have this, the base, right, has changed back to be greater than 1, and therefore we can use our normal rules. In this case, the normal rules will tell us, aha, there's a minus sign on the exponent, I will be decreasing like this. If you attempt to do the math problem without changing the base back into a positive, it can be done, but you will have to basically change all the rules that you have learned so far, and that will require extra memorization, which I know most of my students over the past 2 years are not very fond of. Right, so now that my stylus is fixed, we shall take a look at question 2 over here as a practice as well. We have some drug over here, very funny name, phenytoin. I'm pretty sure medically we use the spelling phenytoin instead, as in PHE, referring to phenyl groups, but on a consumer side perspective, phenytoin suffices. So in this case, we have a formula given to us, concentration equals to 4.86 e to the power of negative 0.047 time, and the time is in hours. So for the first part, they want us to find the initial value of c. So we will simply use time equals to 0. This will give us e to the power 0 over here, and we will get 4.86. You do not need the units micrograms per milliliters over here, because the question only asked for the value. They didn't ask for the concentration. right? There's a difference between the value of x versus the meaning behind the number x. In this case, they only want the value. If you want to include the units, of course, it's completely fine. But again, it is unnecessary. Now, the second portion then asks for the concentration of phenytoin 1 day after administration. Now, 1 day over here naturally will be 24 hours. In other words, the time t equals to 24. So we shall have 4.86, that's a decimal, e to the power of negative 0.047 multiplied by 24. So this entire chunk, you can then feed the whole thing into your calculator, right? Now this is obviously something that even I cannot do mentally, so I'm going to have to smack on the calculator quite often today. So in this case, 4.86 e to the power of negative 0.047 times 24, we're going to get 1.5730. From here, then we can round it off to 3 significant figures. This time round, the question is asking for concentration, so please remember to give units. Now the third part starts to get more interesting. It says state the concentration of phenytoin as the time t becomes very large. So you can informally imagine it as something like this. Let me first clear the screen. I have too much writing going on here. I'm going to need a lot of space. So as a demonstration and explanation of what to do when the question asks for the time going to infinity or going very large, at this level, you do not need to use the mathematical concept of limits to infinity. That is not necessary, right? That will be overkill, honestly. So what we shall do instead is, it suffices for us to informally ask ourselves, what happens if I have c equals to 4.86 e to the power of negative 0.047 times very large? Those of you who are laughing right now, stop laughing, shame on you. This is so immature. So I'm going to have 4.86 e to the power of negative, and if you look at this portion over here, inside the orange brackets, it is 0.047, a positive decimal, multiplied by a very large number, the largest number you can imagine. Maybe 10 to the power of 10 to the power of 10 to the power of 1000 or something like that. So in this case, when I'm multiplying by 0.047, the impact will be very minimal. Right? Let's say I give you 10 to the power of 200 multiplied by 0.047. Even if we rounded this off to 10 to the power of 200 multiplied by 0.001, and this is a very lousy round off, of course, this is cheating myself, right? Like I'm scamming myself. Even if we did something like this, using our standard form from EMath, we see that the final answer, 10 to the power of 197, is still very large. It's still gigantic. So imagine what happens when the words very large get replaced with a number close to infinity. It's going to be even larger, and if you have a number like infinity, it won't even be affected at all. So if it won't be affected at all, then we shall still have a very large number, which I will still call very large. Once we are over here, what I'm going to do next is I will change the negative indices to positive indices by moving the entire exponential term to the bottom, like this. And therefore you see the negative on the power is gone. Of course, once we are here, you will see that this bracketed portion is e to the power of very large, in other words, e to the power of a positive large number, which will obviously be very large by itself. And therefore we have 4.86 to the power of very large, which will actually be close to 0. And this will tell us the answer we need. Now, why is it 0? We need to answer ourselves on this question. Now, to be honest, it is not as difficult as it seems. You can actually test this yourself. Right now, what we have is 4.86 divided by very large, right? So you can ask yourself, what happens when I have 4.86 divided by a large number like 10? That's pretty small, right? What if I have 4.86 divided by a larger number? It will get even smaller. what if I have 4.86 divided by an even larger number, let's say 10 billion, right? 10 to the power of 10. So even if I have that, the number will still be positive. It's just that things will get smaller and smaller and smaller. Right? So eventually you can imagine that if I take this 4.86 divided by the largest number you can imagine, let's say for example 10 to the power of 1 million, you can expect it to be 1 over something that's even larger. And so far what we see is that the denominator keeps increasing. Now the key then comes in converting everything to decimals. So half over here will be 0.5, 1 over 20 will be 0.05. You see that we have decreased, right? And over here, 1 divided by, that is a large number, 1 divided by 2 billion, right, is going to give us 0.00000000005. So once again, I have decreased, and 4.86 divided by 10 to the power of 1 million, we shall not talk about that. It will be too small. So the moral of the story is that large multiplied by a number will not actually make that much of an impact. But if you are dividing by large, then you can expect the number to go to 0. So allow me to informally summarize. We shall have the following. A large number, let's say infinity, multiplied by anything will still be infinity. A large number plus minus anything will still be infinity, because anything is too small relative to infinity, so it doesn't even make much of a difference. And last but not least, anything divided by infinity will give us 0. Again, all of this is informal. You don't need to do the working out. Neither do you need to write everything as a limit, right? So if you want to do limits, then you can write something like this, for example. But this is wholly unnecessary. L-I-M. Yeah, this is entirely unnecessary for our secondary school syllabus. Right, so to answer this question, it says state the concentration as we become very large. In this case, we will have 4.86 over e to the power of, let's see, 0.047t. Right, so I'll remove the negative on the exponent. From here, if t becomes very large, you can see that we have e to the power of 0.047 infinity, which will be 4.86. Multiplied by infinity doesn't change anything, so we have e to the power of infinity. E to the power of infinity will obviously be infinity, and this will give us a number divided by infinity, which gives us 0. And therefore, the final answer, or rather, the immediate answer, because it says state, so there is no working to be done. So all we need to do is to simply tell them, wham, 0 micrograms per milliliter, and we are done. The last part will then be to draw the graph. Oh, don't make my mistake, it's not x, it's going to be t on the horizontal, c on the vertical. In this case, it is very clearly just a decreasing exponential, so we shall have the following. Make sure to label the y-intercept. The y-intercept will be the initial value of c that we found in part 1, because that was when t equals to 0. And then afterwards, label the graph. And we are done. Right, so once we're done with all that unusual indices stuff, the next topic, or rather subtopic we will be moving on to, will be a lot more dramatic. So what we will be going on to is logarithms. Right, so before I begin, I will be taking a short break. I gotta grab some water, so I will see you in a few moments. Alright, what is up? Ladies and gentlemen, let us continue. Now, from here on forth, we will be moving on to the main meat of the matter, right? This is what I am going to be focusing the bulk of today's efforts on, right? We will be beginning our introductory exploration on indices and logarithms, and then we will see how they interplay together. So first of all, we need to recognize what logarithms are. So logarithms simply work like this. They are another way of writing the same sentence. So for example, instead of saying I gave an apple to Mr. Tan, we are writing Mr. Tan received an apple from me. Same meaning, effectively same sentence, different words, different order, right? So you see that y equals to a power x changes to x equals to log ay. An important thing to take note of is that when you have the simple object on the left hand side and the difficult object on the right hand side, then by design the order, which is y a x, will be swapped into x a y. And of course it makes sense that it will be swapped. Are indices and exponentials not designed to be, indices and logarithms not designed to be complete opposites? So because of that, we will see this change. There are a few things to be wary of. First of all is that the number below the logarithm, a, will share the same terminology as indices. This a will be called the base. Instead of being the base of the exponent, we will call it the base of the logarithm. And of course, this base will follow similar rules. I cannot be equal to 0, I cannot be equal to 1. And then for convenience sake, to avoid the up down changing of the plus minus sign, I will fix a to be greater than 0. Right? Another thing to be aware of is that the number within the logarithm itself, so in this case y, will be equal to a power x. And if you recall, a power x from the graph, right, is always greater than 0, which means that y is also greater than 0, like so. As far as real numbers go, you cannot use logarithm on a negative number. You cannot use logarithm on a 0. It will give you a math error instead. Those are not real numbers. By the way, there's a bit of a typo over here, although it's not for a very important section. It says over here that x is greater than 0, but this is actually actively untrue. You can try it in your calculator right now. For example, log 1 over 100, you should get negative 2. Right? So please help me ignore this guy. Okay, so the next thing we will be moving on to is to talk about some of the basic rules first, right? So an important thing to know is that if I have logarithm base a of an exponent, the logarithm and the exponent are supposed to be polar opposites, so they will cancel each other out and leave behind n. This is the first rule. You can imagine this as doing 3 multiplied by 5 divided by 5. Multiplication and division are supposed to be opposites. They'll cancel each other out. You still get back 3. Over here it's the same thing. The logarithm and the exponential cancels each other out. And before I move on to the second bullet point, I want to point out that the opposite order is also true. If I have an exponent first and then a logarithm second, they will still cancel each other out, leaving behind whoever is left on the back side. So logarithm first, exponent second, cancel, cancel. And on the left here, exponent first, logarithm second, you will still cancel, and you will still get the leftover x. Right, so this is a useful tactic as well to simplify some math problems. So aside from that, a few other generalizations, or rather, not generalizations, the exact opposite. A few other specific cases is that if n, which is the number that is on the exponent, if n is equal to 1, then this part here will simply turn into a, and that part here will simply turn into 1. And the last specific case is if I have n to be equal to 0, then this guy here, a power n, turns into a power 0, which is 1. And that guy here, which is n, will simply turn into 0. So these are some specific cases. And over here, a few examples of working out the values of these given logarithms are given to us for us to take a look at. Honestly, quite straightforward. I don't have a lot to say. Let's just take a look at the last one as an exercise. It is a little bit tricky, but you will hopefully be able to tell that we actually have, in this case, 4 to the power of 2.5 to be equal to 32. And obviously the other one will simply be 7 to the power of 3 equals to 343. From here, right, if you remember, logarithm and exponential will cancel each other out. Logarithm and exponential will cancel each other out. And we are done. Now, in our syllabus, and this is not true all the time, this is only for secondary school A math. In our syllabus, two common numbers that we use as the base for a logarithm is 10, which will be short formed as LG or log, as well as E, right, 2.718, which will be written as ln, ln, the natural logarithm. So two very simple examples are given over here. I will not discuss them in detail. Now this next section starts to get even more exciting. We have over here the laws of logarithms. So in this case, we have 3 different rules that we need to follow, and these rules are actually very similar to what we have seen in indices. So for now, before I go through them, let me go back to the start where we looked at the laws of indices that you learned in eMath. In particular, pay attention to the first 2. We see that a multiplication, right, am times an turns into an addition, right? The multiply becomes an addition on the inside. So times becomes plus on the inside. Similarly, divide, right, an over an equals to an divide an. Similarly, a divide on the outside turns to a minus on the inside. And why shouldn't it? Divide is the opposite of times, and minus is the opposite of plus. So these are opposites. Right, so let me say it again. A times on the inside becomes, or rather a times on the outside becomes a plus on the inside. A divide on the outside turns to a minus on the inside. Right, so all these external times and divide connecting multiple different exponentials with the same base, we will go on to simply combine all of the indices together to get a singular gigantic exponent, and then all the times and divide changes to plus and minus. So why am I coming back here to remind you of this? The reason is because logarithms are the opposite of indices. So in indices, what we saw was a times on the inside became a plus, no sorry, a times on the outside, let me write it down actually. A times on the outside became a plus on the inside. So over here we shall do the opposite, right? A plus on the outside becomes a times on the inside. Right, so instead of separate exponentials with a times becoming a combined exponential with a plus, separate logarithms with a plus combine to become a combined logarithm with a times. So the process is opposite, which makes sense because logarithms are defined to be the opposite. Similarly, a divide on the outside turns to a minus on the inside for exponentials. So for logarithm, it will be the opposite. A minus on the outside turns into a divide on the inside. Now, all of these properties will not be given to you, so I'm afraid you're going to have to memorize these, which is why I want to point out the oppositeness of these particular laws. There is one other law, which is not as related, which simply says that if you have an exponential on the inside of a logarithm, the power can be taken down and out. So down in the sense that it's no longer on top, it's no longer an exponent. Out in the sense that it is no longer inside the logarithm. Right, so you completely vanquish the exponential. Take it down, take it out. So some example problems have been given for us over here in order to just simplify the numerical values. Honestly, they are pretty straightforward, so allow me to just go through maybe the first one. The first one tells us we have log 2 40 plus log 2 0.1 plus log 2 1 over 4 plus log 16 8 log 16 4. Now over here, the first three objects are all log 2 and they are separated by a plus, allowing us to perform our laws of logarithm and multiply them together. Over there, we will need to be a little more creative in how we deal with this. So over here you see 16 and it changes into 8, right? So we have log 16 and then the 8 here, right, is actually going to be 16 to the power of 3 over 4. You can check this with your calculator if you'd like. The second one should be way easier. That is the square root of 16. So we will have 16 to the power of 1 over 2. Like this. Once you have this, then the orange portion will simply give us log 2, 1. And the grey portion will simply give us 3 over 4 divided by 1 over 2. However, the logarithm of 1, log 2, 1 in this case, will always be 0, if you remember from earlier. And of course, 3 over 4 over 1 over 2 will simply give us 3 over 2, and therefore our answer is 3 over 2, alternatively 1.5. Right, so pretty straightforward. I don't have a lot to say. It is a little bit annoying to try and do the conversions of, let's say, log 16, 8, right? And you have to figure out 3 over 4 is the power. So in order to avoid having to do all the guess and check on the power, there is one last rule in logarithms that we can use, namely the change of base rule. So let me direct your attention to this particular situation here. In this scenario, what we see is that I can simply change the number below the logarithm, right? If I have log anything and the person being affected, the strategy is step 1, change the base immediately from A to C in this case. Step 2, copy over the original victim. Originally, B was being attacked by log A. So in this case, we will still carry over B, except he will now be attacked by log C. Step 3, put a division. Step 4, copy the same logarithm again. Step 5, use the last letter that you haven't used yet in this case a. So a few examples have been given for us in this particular situation. Let's look at the first one. It says log 5 100 equals to LG 100 over LG 5 equals to 2 over LG 5. So step 1, change the base immediately. Step 2, copy over the same victim 100. Step 3, add a divide. Step 4, copy the same logarithm a second time. Step 5, use the last number we haven't talked about. Obviously this will then give us LG 100, LG 5. LG 100 will give us 2, and we will have 2 over LG 5, which is what the example states. Right, so aside from that, we have 2 other examples over there. I will leave you to review that for yourself. And one simple exercise over here is given. They want us to numerically evaluate all these funny little logarithms without using a calculator. So a little bit of a fun challenge for us. In this case, what we will see is that you might have an easier time if you simply, force everybody to become the same object. In other words, if you were to continuously use the same base. So let's say we try changing everything to LG. So let us look at the first person. The first person, let's use red. This is the first person. So step 1, change the base. I'll use LG. Step 2, copy over the original victim. Step 3, divide. Step 4, same logarithm. Step 5, the last number that we didn't talk about, which is 6. Right? Afterwards, we have the second person. So step 1, LG. Step 2, the same victim. Step 3, divide. Step 4, the same new logarithm. Step 5, the last number we didn't use. And then so on and so forth. See if you can perform this by yourself. Right, so this is what we will have. From here, then we will be very happy because you will see that LG6 here cancels over there and LG3 here cancels over there, like so. Once we have this, there is something even better that we can enjoy, namely that over here, LG10 will simply be equal to 1. And last but not least, we will observe that LG4 over here is LG2 square, which will give us 2 LG2, because if you remember, a power can be moved down and out. So from here, we will have 1 over 1 times 1 over LG2 times 1 over 1, the third person got a double cancellation, times 2 LG2. Like so. From here, it is apparent that we can cancel the LG2 here for the LG2 there. And of course, multiplying by 1 over 1 is useless. Let's get rid of that. Multiplying by 1 over 1 is useless. Let's get rid of that. 1 on the numerator multiplied by 2, right? In this particular section, 1 times 2 will simply give me 2, and that is the final answer. We are done. Not bad. We ended up having to use all colors of the rainbow. Very nice. Alright, so moving on. The next thing we'll be talking about is algebraic problems that have logarithms inside them. So if you have an identical logarithm, right, for example, it's log a with the coefficient n, log a with the coefficient n, we can just cancel both of them out and say that p equals to q. So for example, if I have log 3x equals to, let's say 2, then I can change it to log 3 9, and then I can say that x is equal to 9 because I cancel out the log 3's. Aside from that, we can also use logarithms to cancel out a power. For example, if I give you e to the power of 2x equals to 7, I will simply say that ln e to the power of 2x equals to ln 7, but What happens when you have logarithm and then exponent? They cancel each other out. So 2x equals to ln 7, x equals to ln 7 divided by 2, and we are done. If the question insists on having you round off the answer, then you will feed ln 7 over 2 into the calculator and then get your answer from there. Right, so this brings me to my next point, which is if you have an exact answer, typically this will be okay, especially if the problem just straight up demands exact form. So you will just simplify the logarithm. There's no need to change the base. There's no need to press the calculator to get a decimal answer that you go on to round off. There's no need to do any of that. Now at this point, there are two things to be careful about, two particular danger zones. Number one, I need you to be careful because your calculator, your scientific calculator, only has LG base 10 and ln base e. So if let's say you have log 27 and you want to change it to decimals, you're going to have to do change of base rule like this and then press this whole thing into your calculator. Right, the second danger area is that just like your certs that we saw 2 videos ago, sometimes you get fake news, right? Some of these answers are BS, and you're going to have to check the answers back with the original question afterwards. Last but not least, this is less of a danger area and more of a trick that you can use. Every once in a blue moon, substitution will make the appearance of the math problem look nicer, which will reduce the careless mistakes you make. But this isn't very crucial. Alright, so some exercises have been given over here. For parts A and B, the work has either entirely or mostly been done. So part A, you can pause the video here, and then we will go on from there. Let's see, question in the chat. Some calculators have custom log base. Of course they do. But in your exams over here, we will not be allowed to use scientific calculators with custom bases. So we are stuck with the common logarithm 10 and the natural logarithm e. So we are a little tight in terms of the options available to us. Besides, if I gave you a calculator with everything, then you wouldn't have to do all the manual manipulation anymore. Then the teachers will have less things to test. So over here, I will ignore the first problem since it has already been done. Let's take a look at the second problem instead. Second problem tells us log 3x equals to 4 log x3 plus 3. So this is actually very funny because the unknown is stuck inside the logarithm itself, right? And therefore, what we will do is we shall deliberately perform a change of base on the 4 log x3, right? And we will get the following. The log x3 underlined over here, I'm going to put it in a box. It will turn into this. Log 3 log 3x. This is convenient because log 3 is equal to 1. So I'll simply have 4 over log 3x, right? The log 3x will stay at the bottom. Therefore, we shall have the following. We shall have Therefore, we shall have the original problem, which is log 3x equal to 4 log x 3 equal to 3. This boxed up person will change into that guy. And from here, if I let y equals to log 3x, then we shall have y equals to, over here, 4 over y plus 3. This is very nice because from here, it turns into a very simple quadratic equation. Right, so we will rearrange it and it shall turn into y squared minus 3y minus 4 equal to 0. Of course, once you are over here, honestly, you are already home free. It is clear to us that we can factorize the values as follows. This implies then that y equals to -1 or positive 4. Once we have this, then I can go on to say that because y is equal to log 3x, it must mean that log 3x is equal to -1 or 4. And from here, if you remember what we did at the very first page of logarithms, we learned how to convert logarithm into exponential. So we will simply do the conversion over here, and we will get 1 over 3 or 81. Right, so one key trick is to know when to stop using logarithms and then convert back into exponential. 99% of the time this will be when you are pretty much already done with the math problem. Right, so when you are done with the math problem and you are able to kind of just swap the form from exponential to, from logarithmic to exponential, and from there you will immediately just get the answer. Right, so once we are over here, don't forget to check the answers that we have received, right, just in case one of them turns out to be fake news, because we must always remember that logarithms are very finicky. You might, for example, get a math error because we are only working with real numbers in this syllabus, don't forget. So if you get a math error in your scientific calculator, instantly you know, okay, never mind, this guy is full of crap. We're going to deliberately ignore him. Right, so in this case, what we will see is that you can actually check the values quite simply by referring back to the original question. I think for 1 over 3, that will be the easier one to check, right? So let me just briefly demonstrate the checking process. So in this case, we have the original math problem over here. If you were to check this, we have the left hand side log 3, 1 over 3 is -1. The right hand side 4 log 1 over 3, 3 plus 3. This will turn into 4 log 1 over 3 on the base, 1 over 3 to the power of -1 on the top, plus 3. And this will turn into 4 multiplied by -1 plus 3. In other words, -4 plus 3. In other words, -1. So we get the same answer. No issues there. Alright? So there really isn't much to it. You simply have to plug in the number that you have found and then slog through everything. If the base is very nice, for example LGLN, then of course you can just feed the whole thing into the calculator. So if we have 81 instead, this will give us 4, and that over here will be a lot more interesting, right? In this case, we will recognize that 3 is simply 81 to the power of 1 over 4. If you can't recognize this, you can simply do change of base. But over here, it is clear that the logarithm and the exponent will cancel each other out, and 4 times 1 over 4 will give us 1, and 1 plus 3 equals to 4, as desired, right? So you can rest assured knowing that both answers are correct. So moving on, we have ln 3x equals to ln 9. This is a joke question. We can cancel out the lns, and this will imply that e3x equals to 9. From here, we will take logarithms on both sides. The logarithm ln will cancel out the e. We will get 3x equals to ln 9. Of course, ln 9 is 3 to the power of 2, so we can move the 2 down and out. And from here, x equals to 2 over 3 ln 3, and we are done. Right, so the fourth problem is a bit of a callback to the problem we just spent a lot of time discussing. So I will deliberately discuss less over here and leave you to fill in the mental blanks by yourself. We are given 2 log x8 equals to 2 plus 2 log x2. In this case, because both of them are log x, we don't need to change the base. We can simply look at the left hand side and change him into log x 2 to the power of 3. And from here, the 2 to the power of 3 is very nice because the 3 can be moved down and out. So we have 2 times 3 log x2 equals to 2 plus 2 log x2. Obviously 2 times 3 over here will be equal to 6. And from here, then I will use my trick. The same object is now repeating, so we will let y equals to log x2 in order to make the math problem look nicer. Now we will have 6y equals to 2 plus 2y. And over here, the rest of the math problem becomes trivial. And therefore, log x2 equals to half. Right? And once we are in this scenario, okay, what we need to do is we are going to convert from exponential back into, from logarithm back into exponential. So I want you to remember the trick that I said at the start, which is if you have the nice person on the left and the ugly person on the right, right? So in this case, the nice person is half, the ugly person is the entire log. Then, in order to convert back into your exponential form, simply swap the order. So in this case, we have half x2. We can swap this into 2x half. And obviously, this will give us square root x. And from here, it is clear that x equals to 2 squared equals to 4. And we are done. Now the last problem over here, at least I think it is the last problem, let me check. Okay, the last problem over here is quite an amusing one. We have 3 to the power of x, 2 to the power of 2x equals to 7, 5 to the power of x. Right, so what I'm going to do is I'm going to leave the 7 alone and I'm going to move him over. That way all the x's will be on the same side. And from here, we have 2 magic tricks we can perform. First of all, this thing can be combined to 3 over 5, entire thing to the power of x. Second of all, this person here, right, is the same as 2 to the power of 2x, which of course is 4x. Once we have this, because both of them have x on the power, right, a times on the inside. No, sorry, this is not actually the same thing. What we will see instead is that we can factorize out the indices. We can factorize out the exponent by using our laws of indices, and from here we will get 12 over 5 entire thing to the power of x. Now this is very beautiful actually, because from here we get a dramatically simplified math problem. So the 12 over 5, right, is equal to 7. So we shall simply change the math problem into 12 over 5 entire thing x equals to 7. Once we are here, what I will do is I'm going to use the common logarithm. And over here, you will see that I can move the power down and out. Like so. And therefore, we will say that x equals to LG 7 divided by the entire LG 12 over 5. And from here, you can feed this into your calculator. Do remember, right, be reminded that on your calculator, we don't say LG, we just say LOG. Right, so you have LOG 7 divided by LOG 12 over 5. This will give you 2.2227, which to 3 significant figures will be 2.22. And that will be our answer. Right, so I will be going for a water break and I will see you in a moment where we will begin to wrap up the topic by talking about logarithmic graphs and then real-life applications of logarithms to solve simple math problems with growing and decreasing items. Once we are done with that, then the content will be done and we will move on to a few extra practice problems and then we will be done for the day. So this will probably be a 2-hour video actually. Okay, ladies and gentlemen, we are back. Now let us begin the last leg of content for today. So what we see over here is we're going to move on to graphs of logarithmic functions. So this time around they're a little bit different from exponential. If you remember exponential, we are increasing at an increasing rate. We are decreasing at a decreasing rate. Right? But over here, it is the exact opposite. What we will do is we will be a lot more pathetic. Instead of increasing at an increasing rate, like a success story, we will increase very enthusiastically, and then we will start to get depressed, and afterwards we'll increase very slowly. It will be the opposite. Similarly, we will decrease very enthusiastically, then we will decrease at an average speed, then we will decrease slowly. In other words, we have the exact opposite of exponential. Exponential increases at an increasing rate. Logarithm increases at a decreasing rate. In other words, exponential is the drama queen that attacks itself, right? I'm rising more, I'm rising even more. Whoosh, that's why we get the exponential graph shape. But the graph of a logarithm function is the opposite. You start off very enthusiastic, right? You start off very happy, then you realize your life sucks, and then you stop putting in effort, and then you feel like crap, and that is the shape that we see over here. Right? I will leave you to read the text on your own. It is not exceptionally difficult to read. Now, for the portion below, this will be more exciting. What we see is that we have a few different details to be aware of. First of all is, because logarithms are the opposite of exponential, all of the positions will also change. In exponentials, we had a asymptote on the bottom. I'm floating above the x-axis. For logarithms, it will be the opposite. I will be floating not above, but to the right of the y-axis. So the logarithm position has flipped as well. Sorry, the exponential and logarithm graphs have asymptotes, but the asymptotes themselves have also flipped. Of course, this also means that your y-intercept will now turn into an x-intercept. So I'll leave you to read the details here by yourself. Now at this point, one other thing to talk about is this bullet point over here. In exponentials, we have seen that when the base is bigger, right, you will get a very dramatic graph. For example, 10 to the power of x is very clearly more explosive, more steep than 2 to the power of x, because 10, the base, is greater than 2. However, if you were to try this with logarithms, because logarithms are the opposite, what we will see is that the one that is 10, which is lgx, will actually be pathetic and flat. And it is the smaller base. It is the smaller base, in this case 2, that will be more explosive, that will be steeper. Because again, logarithm is the exact entire opposite. That is the purpose for its existence. So all of the rules will be flipped, right? So before I move on to the practice examples, again, I want to highlight the linguistic intricacies, right? When we say exponential, it means that the increase, decrease itself will increase and decrease. And in other words, we will say that it is increasing with increasing rate. It is decreasing with, that is horrible handwriting, let me try that again. It is decreasing with decreasing rate. Logarithms will be the opposite. Logarithms will increase with decreasing rate, or will decrease with an let's see, where is, yep, decrease with increasing rate. Okay, let me erase all of this. Right, so over here we have an example at the bottom. They want us to draw lgx and negative 2 ln x. Be careful over here, negative in front of the ln does not mean decreasing with increasing rate. It merely means the logarithm graph, and then I flip vertically. If you remember, a minus sign on the entire algebra means that you will flip vertically across the x-axis. So lgx is straightforward. It will be increasing at a decreasing rate. I will start off fast, and then I will lose my enthusiasm. I will cut at x equals to 1, which makes sense because this is the x-intercept. At the x-intercept, y equal to 0. In other words, lgx equal to 0. And we know that the logarithm of 1 is always 0, so very clearly x is equal to 1. Right? Straightforward. Now the same process works for ln x. The problem here is ln x is multiplied by negative 2. Now multiplying by 2 doesn't make a difference. All it means is that the graph will look taller. So that's whatever, that's negligible. The negative, however, means that I will need to flip myself downwards into the opposite direction. And therefore we will get the following graph instead, which is what you see over here. Right? Now logarithm graphs are way scarier for most of my students than exponential graphs. So I will be covering a lot more exercises over here. Having said that, however, the first few exercises are quite straightforward, so I shall not spend much time on them. I will not be doing the complete labeling over here in order to save time, because this video is long enough as it is. So for the first two examples, they are really lame. The first one is literally ln x, so just draw your standard logarithm graph. Increasing, start to slow down, get disappointed at life. The second problem is the same, it's just that we have two graphs. One is lgx, the other is 5 lgx. The one with a 5 means that all the y coordinates get multiplied by 5. So it will be more explosive, more dramatic, more steep. And for the third problem, we have negative lgx, so you will simply reflect vertically, and therefore we can expect the graph, instead of being like this, we will reflect vertically and it will be like that. Right, so the next few problems will be a lot more interesting, and over here I will need to go back to the top and talk about one bullet point that I deliberately ignored. In all of these graphs so far, we have had some specific criteria, namely that we have made these assumptions. The coefficient is positive and that the base itself is greater than 1. Now, if the coefficient is negative, it's quite simple, right? I will simply go downwards because I will be reflected. But what happens if the base of the logarithm itself is negative? The answer is it will actually have the same effect, and we will flip to go downwards. As a simple demonstration, I want you to consider y equals to log half x. We can actually change this into log 2x log 2 half, which then changes to log 2x over negative 1. In other words, negative log 2x. Do you notice that having the base a be lesser than 1 actually creates a negative sign? And therefore, the graph will be flipped vertically, just like if I added a negative sign. Conveniently, this also means that if we have two screwed up numbers, there's a negative sign in front, and my base is between 0 and 1, exclusive. That means that we will end up producing a second negative sign. The double negative will therefore mean that there was no flipping taking place. We will still go upwards. So let us see this in action. Over here we have y equals to log 0.1x. If you want to simplify this, we could actually do lgx lg 0.1. This turns into lgx lg 1 over 10. This turns into lgx lg 10 to the power negative 1. At this point, the lg and the 10 cancel out, and we'll get lgx over negative 1. In other words, negative lgx. Alright, so what we will see is that over here, the 0.1 actually adds a minus sign where it was previously a positive coefficient. Because obviously the coefficient here is positive 1, right? It's the easiest thing in the world. But that 0.1 in the logarithm, it ruins everything. You're going to end up getting a negative. So over here, now we know it will actually be negative lgx. And just as the previous page states, this will cause a flip, right? So either you look at this and you see, aha, it's between 0 and 1, it will be a vertical flip. Or you do the conversion and you say, aha, minus sign, it will be a vertical flip. In either case, we will do a vertical flip of the normal floppy logarithmic graph. I like to call it something in class that I will not say online. So you're going to have to attend my real life lessons for that. So instead of this, we will flip it over and you will get a downward floppy like that, cutting at 1 as usual. Let's see some comments in the chat. Yep, logarithm is exactly the opposite. Not only are the graphs opposite, right? So for example, asymptote on x becomes asymptote on y, x-intercept becomes y-intercept, and even just the fact that they are formulated in opposites, right? If x equals to log ay, y equals to a power x. So you notice even the order of the algebra is opposite. And perhaps more convincingly, we must also remember that because they are opposites, just like how plus and minus are opposites, times and divide are opposites, they can cancel each other out. So if I have an exponential and then a logarithm, they cancel, you get the leftover. If I have a logarithm and then an exponential, they cancel, you get the leftover. And last but not least, and perhaps the coolest of all, is that the properties themselves are changed, right? So exponentials with multiply change into a plus on the inside. Logarithms with a plus change into a multiply on the inside. So even in the algebra rules, the times changing into a plus will turn into the opposite. We get a plus changing into a times. That's why we say that logarithms and exponentials are opposite. Everything is the exact inverse. For those of you who are smurfing and are not O-level students, you will probably recognize all these as mathematical results created by the fact that the logarithm and the exponential are inverse functions of each other. But we will not talk about that in O-levels. Okay, next problem over here. Now over here, there's a negative, so we expect a flip. There's a half, so we expect a flip. Therefore, the flip will undo the flip, and we will get a very normal graph like that. The end. Oh, the next one here is a little more exciting. We have LG, which is base 10. We have this guy, which is base 25. So if you remember, in exponentials, the one with the bigger base is the one who will explode more, right? But because this is logarithm, and logarithm is the opposite of exponential, the one with the bigger base will actually be flatter. So this will be my log 25x. And the one with the smaller base, in this case LG, will actually be the one enjoying his life. Like this. And of course, the x-intercept is still at 1. Right, so even for the graph drawing, even the steepness itself is opposite compared to exponential. And yes, just as live chat says, if you are good at drawing exponential, you should be good at drawing logarithm. Just opposite everything. And vice versa, of course. Right, so over here, next problem is pretty interesting. This guy here naturally turns into y equals to log 6x. Please remember how to do the conversion. And therefore, we will have the same issue as just now, where one person is very flat, and the other person is having the time of his life. He's exploding. Alright? Now the next few problems are extremely advanced. Let us look at them and think about what happens. We have y equals to lg x plus 2. Now typically, this will be lgx. It cuts at 1. It has a forbidden line at x equals to 0. The reason x equals to 0 is forbidden is because lg0 is a math error. And the reason why the x-intercept is at 1 is because lg1 equals to 0. But what happens when you have lgx plus 2? In lgx plus 2, we will see that the rules of the game have changed. Now, if x equals to -1, then I'll get lg1, which will then give me 0. In other words, -1 over here will be the x-intercept. And of course, if I have lg -2, then I'll have lg0, which is death. So -2 here will be the asymptote. In other words, you notice that everybody, right, has moved backwards by 2 steps. The 1 has moved into -1, the 0 has moved into -2. Everybody has moved back by 2 steps. Now, because we haven't learned about graph transformations at this level, and we do not need to learn it for O levels, what I like to call this is compensation effect. When the person suffering from the advanced mathematics, in this case suffering from the logarithm, the person suffering is x. When the person suffering is inside a bracket with a plus minus, we will need to compensate for the plus minus. In this case, it is +2, right? It is +2. In other words, this algebra already starts off with a free of charge +2. In order to ensure fairness, we must compensate for the +2 by moving everything 2 units behind. In other words, we compensate for the +2 by performing a -2. And this will apply to the asymptote as well. So x equals to 0, right? We will do a compensation -2. And we will get over here instead x equals to -2. Then from here, you can draw the graph. So with a new asymptote, with a new x-intercept, and then we will go on this way. So this compensation will go -2 in the x direction. X direction because the +2 is attacking x. So we will do compensation on the x direction. So cleaning all of this up, our final answer will therefore be something like this. Like so. Of course, do notice that because the graph moved to the left, we now have an y-intercept as well. So you're going to have to find this y-intercept. If you remember, a y-intercept is when x equals to 0, so we will simply have LG2. Now if you want to press your calculator and get 0.301, that's completely fine. For me, I'm the math teacher, so I'll be lazy. I'll just write LG2, like so. Now you are allowed to do this as well. Remember, we're in A math. A math is completely fine with exact form. So the last problem here that is important and frequent enough for us to pay as special attention to will be this guy. This guy is actually quite simple. You notice the plus 3 is not attached onto the x, it's not attached onto the logarithm with a bracket. It's simply a plus 3. So what happens when we have a number? If you remember, we will simply either move up or move down. In this case, it's a plus 3, so we can expect that the graph moves upwards by 3. So you can imagine this is LGX. Okay, from here I will simply plus 3 and move up like that. Right, so instead of going along the x direction like the previous problem, this time around it is simply along the y direction. And let us clean up the diagram. The final answer will therefore look like this. And at this point you will tell me, wait a minute, doesn't this just look like the same exponential graph as always? And my answer to that is yes. Yes it is. So actually this is a joke question. The only thing I need you to be careful about is the x-intercept. Remember, at the x-intercept we will set y equal to 0. If you set y equal to 0, you'll get 0 equal to LGX plus 3, LGX equal to negative 3. We will then convert into exponential, which is that, let's see, 10 equals to, wait a minute, I should actually write it in the same format as always so that you can follow along. My mistake. So let's write it as the nice person on the left, the ugly person on the right. Then we can convert this and we will say that x equals to 10 to the power negative 3, in other words 1 over 1000. And therefore this number here will no longer be 1, it will be 1 over 1000. And we are done. Alright? So the next thing we need to take a look at is some certain situations in real life where we can expect to use some, shall we say, we can expect to use some logarithms in our sciences or in our statistics, so on and so forth. So in this case, this exercise given over here is to introduce the idea of how pH in chemistry, when we measure acids and acidity, is actually created by the common logarithm Lg. Of course, this is a pretty simple example, so I will leave it as an exercise for you to review. Let's take a look at the second one. The second one here tells us, okay, I have some money, I put it into an investment fund, and the number of millions of dollars is capital A. It is equal to 9 times 1.12 to the power of t. T is the number of years. So be careful of all these units, right? Otherwise, you might make assumptions. For example, you might think, oh, maybe t is the number of months. No, it's the number of years. So the first part asks for initial. And hey, if you remember, we've actually seen this kind of question before, around 1 hour and 20 minutes ago in our real life exponential function problems. Over here it's the same thing. If you want initial, that means time has not started flowing. In other words, t equals to 0. And therefore a will be equal to 9 times 1.12 to the power of 0. Obviously this will be equal to 9. In other words, we expect an initial of 9 million. Don't forget to answer the question and tell me $9 million. Don't just say 9. Alright? Remember, math Exams are customer service. Give them what they want. Second part asks, after how many years will the amount in the fund be doubled? Now, doubling will simply mean that we now have $18 million. So capital A will be equal to 18. So we have 18 times, or rather 18 equals to 9 times 1.12 whole thing power t. Clearly, 1.12 to the power of t will be equal to 2. From here, I am going to add in a logarithm. And this is nice because the power can move down and out. So I will get t multiplied by Lg 1.12 equals to Lg 2. From here, t will obviously be equal to Lg 2 divided by Lg 1.12, and this will give me my number which can be used to write the final answer. In this case, you'll realize I'll get 6.116. And therefore, remember to answer the question. The question didn't ask for capital T. The question asked how many years. So we will say it will be double after 6.12 years to 3SF. So once we have this, then the next problem will then be, they want us to sketch the graphs of A against T and then T against A. So this will be very interesting because the problem given to us right now is an exponential, which means when we do T against A, which is the flipping, we are going to have to flip the exponential into a logarithm by our own hand. So let us try it out. We will start with the easy one, A against T. This should be pretty trivial, I would say. So A against T will simply be a classic A against T will simply be a classic situation of the exponential graph. In this case, what we will see is that it will very obviously be an increase, right? We should have the following scenario. As a reminder, if I say A against T, that means that the first person A is Y, the second person T is X. Right, so it is as easy as it gets. It will be your classic exponential. Make sure to label the intercept, which will actually be the initial amount of money inside the fund, 9. Well, 9 million rather. Right, now conversely, part B will be more interesting. If you want T against A, that means, very understandably, we will have this instead. In order for us to work this out, we are going to have to do the conversion by ourselves. So let us start with making capital T the subject by isolating the 1.12 like this. Once we have this, then clearly we have the following result. And you might be thinking to yourself at this point, wow, this looks like S. Why is the base 1.12? What do I do? But don't worry. The base here, 1.12, is greater than 1. So you don't have to worry about any extra flipping. As far as you need to know, this is the same logarithm graph as always. Like this. Afterwards, don't forget to label the intercept. It will conveniently be 9. So at this point in time, I would like to point out a coincidence, which is that if you were to draw the two graphs on the same diagram, you will notice that because exponentials and logarithms are genuinely opposites of each other, they will be reflections of each other, mirror images of each other, across the line of conversion itself, y equal to x. Of course, you don't need to know this, but it's pretty fun. Right, so congratulations, up to this point in time, I am done with the main body of content. Now I will move on to some extra practice questions. So If you have been watching up to this point so far in a single day, honestly, this might not be a bad time for you to take a break or even just call it a day. But if you have the guts to move on, then let's move on. For now, you can enjoy this image. I will go for a water break and I will be back in a moment. Alright, ladies and gentlemen, welcome back. We will now be moving on to our practice problems, some bonus exercises for us to look at. For those of you who are really confident with this topic, I'm going to be honest, you can probably skip through this. Right, I'm going to be perfectly frank. Okay, so today we have 6 problems given to us. The first few are all very algebraic and theoretical in nature, so I don't have too much to say. Right, so let's take a look at question 3. Question 3 tells us to sketch a certain exponential graph, and afterwards the second part asks us, can you sketch a straight line, and thereafterwards go on to state the number of solutions. So before we begin, of course, let us recall that when you have 2 graphs together on the same diagram, the number of solutions will be given by the number of intersections. Right, so if the graphs cut each other 2 times, that's 2 distinct real roots, 2 distinct solutions. Right, so for 3 part 1, I'm going to be honest, this is really not going to be a challenge. Right, in this case, what we see is it's 3 multiplied by 2 to the power of x. 2 to the power of x is your standard exponential, the one that enjoys life. It is increasing at an increasing rate. Always remember, exponential is increasing, increasing more, exploding. Logarithm is increasing, realizing life sucks, getting depressed. Increasing with increasing versus increasing with decreasing rate. Alright? So, having said all that, make sure to label the y-intercept. In this case, the y-intercept will simply be, we will substitute in x equals to 0, and therefore we shall have 3 over here. Right, so honestly quite straightforward. So in this case, what we will be more interested to do next will be the second part. Second part asks us to sketch 6 minus x, and then afterwards they want us to find the number of solutions. This is actually a bit of a joke question, because 6 minus x is like, come on, you guys learned linear graphs at what, 12 years old? You have nothing to be afraid of. So the y-intercept here will be 6. The gradient will be -1, and therefore we can expect the graph to be a downward straight line like so. Of course, in this case, then we will notice, hey, there's only one intersection, and therefore we easily conclude that one intersection implies just one solution, and we are done. doesn't get much simpler than this. So this is a very delightful 4 marks for you to have. Now the next problem, question 5, is actually not on logarithms, it is on indices, right? Your manipulation of all the exponents and all that. So I will not spend a lot of time on this. The only fun part of this is that it is not exponents by themselves, it is actually a series of simultaneous equations that are embedded inside. Fortunately, our strategies will still be the same, elimination and substitution. And as you all remember, I always espouse using substitution in our classes. So let's begin. Over here we have 5x multiplied by 25 raised to 2 times y equals to 1. 1. You can't even do anything much with 1. So what we're going to do here is, this green colored portion here is clearly equal to 5 square 2y, which then turns into 5, 2 times 2y, in other words 4y. So we will change this to 5 power x times 5 power 4y equals to, and over here we're going to do a pro gamer move. If you remember, anything to the power of 0 equals to 1, and therefore 1 can also be equal to 5 to the power of x, where x equal to 0. So in other words, I'm just going to slap 5 to the power of 0 over here. And this is very nice because I can then change the left hand side into 5x plus 4y equals to 5, 0. Once we are at this stage, it is really straightforward for us to simply close one eye and ignore the presence of the base. And from here, we will see that, of course, we get x plus 4y equals to 0, from which it implies x equals to -4y. And we will then call this equation 1. Once we have this, let us move on to the next person. The next person tells us, oh, that is ugly. 3 to the power of 5x, open bracket, 9 to the power of y, close bracket, equals to 1 over 9. Fortunately, over here, I think this is actually more straightforward. 9 to the power of y clearly will be 3 square, whole thing to the power of y. In other words, 3 to the power of 2y. Over here, we have 1 over 3 to the power of 2. In other words, 3 to the power of negative 2. And hence, we have 3 to the power of 5x multiplied by 3 to the power of 2y equals to 3 to the power of negative 2. This implies then 3 to the power of 5x plus 2y equals to 3 to the power of negative 2. From here, of course, we will compare the powers again and get 5x plus 2y equals to minus 2. We will call this equation 2. From here, we will perform substitution of 1 into 2. In other words, 5x plus 2y equals to minus 2. Now, once you are here and you have done the substitution, you've already won, if I'm being honest. From here, it defaults back to what you learned when you were 13, 14 years old. Your typical simultaneous equations, which we have seen in the past few videos, right? So from here, you will simply go on to solve for y. Let me see, you should get y equals to 1 over 9, assuming my mental sums are correct. And from here, we will call this number 3. Let us substitute in number 3 into the very first guy, number 1. This will give us x equals to negative 4 multiplied by 1 over 9. In other words, negative 4 over 9. And once we are here, then we are done. Therefore, x equals to negative 4 over 9, comma, y equals to 1 over 9. Boom. Alright. So, the second problem, 5b, is more or less the same thing. So I will leave that as an exercise for you to try out on your own. Now let's look at question 7. 7 is actually very interesting, because we are not exactly finding the value of x. Instead, what we are doing is they have given us some numbers and they want us to turn it into algebra with p and q. Instead of finding the algebra as a number, we are finding the number as an algebra. Exciting. So they have told us that LG3 equals to P, LG5 equals to Q. The first problem we have is LG45. Now fortunately, 45, if you recall how to do your prime factorization, can be easily split apart, because it is actually equal to 9 times 5, and 9 itself is 3 squared. So we have the following. Now this is delicious because logarithms with a multiply on the inside, if you remember your laws of logarithms, can be split apart, changing it into a plus. As a reminder, this is the exact converse of what we have seen in exponents, where if I have if I have a multiply on the a plus on the inside, it changes into a times, right? So observe the difference in the conversions taking place. Okay, so once we have gotten this, we are more or less already done. Do recall that the power, in this case 2, can be moved down and out, and this will produce for us the following result. And from here, as we said, LG3 is P, LG5 is Q, and hence we have 2P plus Q. And we are done. Okay, so once we have this, the next problem will be log 7510. So some people see this and they're gonna panic because, whoa, 75, that's like huge, dude. But in actuality, we don't really have too much to be afraid of. What we will do is we will simply invoke change of base. Now, very clearly the final answer you want is in P and Q. And P and Q are represented by LG, base 10. So let's change everything to base 10. Step 1, change the logarithm. Step 2, same victim. Step 3, division. Step 4, write down the new logarithm again. Step 5, copy down the last number you didn't care about. From here we get 1 over LG, and then the 75 once again can be split. It is 3 times 25, in other words 3 times 5 squared. And this will give us LG3 plus LG5 squared. Of course, 5 squared, we can move the power down and out. So we should expect to see 2 LG5. And from here, once again, LG3 is P, LG5 is Q. We shall have 1 over P plus 2Q. And we are done. So we're starting to use some really gamer moves. Part A was straightforward, right? It's just, what, 2P plus Q. Part B, you notice the algebra is now in the denominator. And part C is going to be even more of a gamer move. Look at how they're asking for a whole number, 375. So most people, they see this and they instantly give up. Hey, the question logarithms, yeah, how come they give me number? What the? Please don't have this kind of mentality. Think about it. Numbers should be a good thing. Ever since you were in primary 5, primary 6, right, when you were 10 years old, the moment your age hit double digits, people started asking you funny questions. Shapes and letters started turning up in mathematics. Why is there X? Why is there 2 circle plus square equal to 420? Right? So if you see a number returned to you, and it's a nice number, 375, wow, no decimal, no fraction, you should be happy. So let me show you how to be happy about this. First of all, the question itself is a whole number, right? And what you have with you, in your left hand, log 3. In your right hand, log 5. You're not even on the same dimension right now. So bring the fight to them. Change it all into numbers. How do we do this? We will change it into numbers by changing logarithm into exponential form. So let's take a look at this guy. We will have P equals to log 3. I will write the 10 here for illustration purposes. And we will change this into exponential. Always remember, if the nice person is on the left and the ugly person is on the right, we can just switch apart the order. So P 10 3 turns into 3 10 P. So we shall have 3 10 P equal. Now your left hand is no longer holding log 3. It's now holding 3. And you will notice that 375 can be divided by 3, correct? So from here, I believe you know what to do for the rest. We will have Q equal to LG5. Therefore, 5 equals to 10 to the power of Q. 10Q. Chimata. From here, we have 7 part C telling us to start with 375. 375 here, we will perform our prime factorization again. You will realize it is equal to 3 multiplied by 5 cubed. Once we are here, 3, right, will be replaced with 10 to the power of P. I should make this thing thicker. Once you are here, 3 will be replaced by 10 to the power of P. And of course, 5 will be replaced by 10Q. So from here, we go on to get 10 to the power of P multiplied by, and then afterwards 10 to the power of Q. Don't forget to include the power 3. From here, of course, 10Q to the power of 3, this guy will simply be equal to 10 to the power of 3Q. And therefore, we have 10 to the power of P times 10 to the power of 3Q. In other words, 10 to the power of P plus 3Q. And this entire thing will be your final answer. And we are done. Right, so this will be our strategy here. Don't get intimidated even if they give you a whole number and you're struggling to figure out, wait a minute, My left hand is log, my right hand is log, but the dinner table, whole number. How now, brown cow? Simply convert it into whole numbers as well, right? The logarithms, change it into exponential form. You will then get a converted whole number, and then you can take the fight to your enemy. Alright? Okay, now that we're done with that exciting problem, unfortunately we're moving back to some really resident sleeper stuff, right? Let's take a look at question 9. Question 9 wants us to find the value of x. Notice they're asking for exact values. So great news, guys. You do not need to press it into your calculator and get a decimal answer and round it off. It's fine. We will simply go full algebra on these guys. So let's take a look at 9a. 9a tells us 2 to the power of 2x equals to 12 plus 2 to the power of x plus 2. In this case, what I will do is I'm going to rearrange the indices. 2 to the power of 2x is equal to 2 to the power of 2 holding to the power of x, which is equal to 2 to the power of x holding to the power of 2. I will use this form. Right? As for the right hand side, I will have 12 plus 2 to the power of x, and then because it's plus 2, I will multiply by 2 to the power of 2. Clearly, this will simply be multiplication by 4. Once you are here, I believe you know what to do next. We are going to do a substitution trick to make the math problem a little easier to look at. I will let y be equal to 2 to the power of x, and so y squared equals to 12 plus 4y. From here, the rest of the problem should be pretty straightforward. We will have y squared minus 4y minus 12 equal to 0. And afterwards, I shall perform the usual quadratic factorization strategies. Oh, sorry, it should be negative, I think. Negative? Yeah, negative. And from here, we will have y equal to negative 2 or 6. And of course, if you recall, we said y equal to 2 power x. And 2 power x is an exponential. If you remember your exponential graph, it will be greater than 0. So we will only accept 2 to the power of x equals to 6. We will reject negative 2. From here, x will clearly be log 2 6. Convert the exponential form into logarithm form, and we are done. So the second problem here is a little more silly. We are given 2e to x plus 15 ex equals to 13e to x. So without anything, let us first change the right hand side to 13 ex squared by using the same method as we saw in exercise 9a. Now once we have this, I'm going to deliberately divide everything by e to the power of x, because e to the power of x is an exponential. He's always positive. We do not need to worry about the possibility of dividing by 0. Therefore, we can safely divide, and this will give us the following result. From here, I think you know what to do. Again, the e to the power of 2x can change into a square, and I'm also going to move everything onto the left hand side. Now, typically, this is the point where you will let y equals to e to the power of x, and then solve the quadratic. For demonstration purposes, I just want to show you the working if you do not do that. The truth is, it will still exactly be the same thing. We will simply pretend that our substitution y never happened, and we will do the entire thing with e power x. Like this, and we are done. Of course, you should put these values back into the original problem and check to make sure there are no fake news answers. In this case, from what I recall, both of them are correct. The next problem will indeed have fake news, however. So let's take a look at 9 part C. 9 part C tells us we have log 3x minus 5 plus lg 2x plus 4 over lg 3 equals to lg 100 plus 2 log 3 2. That is not a 2. 2. There we go. It's hiding underneath the blue button. So what we're going to do here is, first of all, right, if you look at this guy, he is an absolute disaster. Right? The top is algebra, the bottom is a bunch of unrelated numbers. But let's take a look closer. Let's take a look closer. Do you realize we have a different base, the same victim, a division, the same modified logarithm, and one last number that was ignored? This actually aligns perfectly with the steps of change of base. Remember, step 1, create the new logarithm. Step 2, have the same person. Step 3, divide. Step 4, copy the same new logarithm. Step 5, write down the last number we didn't think of. Compare them. It is apparent that small letter c here in this case is 10. And of course, A will be 3, B will be the algebra. And this allows us to work backwards and use this guy instead, log AB. So how does this look in actuality? Let me write it out for you. We will observe that this guy here will actually be log 3 2x plus 4. Because he will then turn into LG 2x plus 4 over LG 3 as desired. Alright, so that will be our first step. In doing this change of base, it will be a very powerful strategy. Oh, I pressed too many undos. Let me bring it back. There we go. Technology. Wow. So what we will do is, step 1, perform change of base, or rather undo the change of base on the second object on the left hand side. You're going to have to think quite out of the box for this one. As for the right hand side, LG 100 is a joke. You can press this in your calculator, it's just 2. As for 2 log 3 2, right? Do you notice this guy in front is down and out? So we can undo the power law and bring him upwards and get the following result. You might be thinking to yourself, okay, but why would I do that? Answer is simple. Look at the left hand side. Everybody is log 3 and everybody has a coefficient of 1. There is no extra. So we shall get rid of the extra by taking the 2 in front of log 3 on this guy. We're going to take this 2 and we're going to force him inside in order to get rid of the extra. Therefore, my coefficient here will now be 1, just like this guy in the middle and this guy in the far left. Everything will now be 1 as the coefficient. This standardization will allow you to solve math problems more easily. Once we are at this stage, the left hand side consists of 2 logarithms with a plus and the base is the same, allowing us to do multiplication inside a single combined logarithm. Right? As for the other side, we have 2 plus log 3 4. Now once we are here, what I'm going to do next is I will open up the brackets over here. We shall get 2x squared minus 6x minus 20. Thereafterwards, I will take all the logarithms and put them together. All the numbers, in this case there's only one number, 2. All the numbers, put them together. We shall get the following. And this is very nice because the left hand side now has log 3, and a minus. In other words, it will simply be changed into division. Right, and from here we can then convert it from logarithm form into exponential form. like so. Right, so once we have this, we will go on to simplify the, I just realized the 2 became a 3, my mistake. There we go. Once we have this, we will simplify the left hand side a little bit, and we will get the following. From here, we will simply move the denominator like that, and this will give us a quadratic in this particular shape. From here, then the rest of the problem is pretty straightforward. We will simply perform quadratic factorization as always, like so, and this gives us x equals 7 or -4. Right? Now remember, always check for fake news. In this case, I will tell them in log 3x minus 5, comma, and log 3x minus 5 came from the original question. Look at the top left. Right? It's not from my working, it's literally the original question itself. So in log 3x minus 5, x equals to -4 causes an undefined logarithm, because you cannot logarithm a negative number, at least not with real numbers. So we will only have x equals to 7 and nothing else. X equals to 4 is actually fake news. Alright. So the last problem over here in this set, part D, I will leave it to you as an exercise. I think you can probably tell what to do, because one side is log 9, everybody else is log 3. So you should probably start with a change of base on part D. After you do change of base, then you can use the same strategies we have used in 9C, and then you will be able to work it out. Right, so help me try that by yourself. Since you have the worksheet with you anyway, you can just check the answers. Alright, we're almost done. Now let's look at question 11. Finally, something fun again. 11 tells us at the beginning of 2020, the population of a town is 12,000, and the population has the formula P equals to 12,000 e to the power of 0.07 multiplied by n. N is the number of years. Okay, so it's a very small town, all things considered. Part 1 asks us, can you find the population in the beginning of 2036 to the nearest whole number? Now, you must recall that we started from 2020 and we're going to 2036. In other words, we moved forward by 16 years, and therefore we will set n to be equal to 16. Right, so n equals to 16 means what? It means that we shall have population, oh wrong color, we shall have population equal to 12,000 e to the power of 0.07 times 16. Now feeding this into the calculator is really simple. You should get 36778.2. From here we will go on to have 36778 people to the nearest whole number, because that is what the question asked for. Always remember, customer service, give them what they want, right? Now, second part asks us, can you find the year in which the population first hits 100,000? Again, customer service, they're not asking for n, they're asking for the year. So we should not have n equals to, for example, 20. You should tell me, for example, 2040 instead. Alright? So in this case, the year in which the population hits 100,000, the population capital P will be 100,000, and this is equal to 12000 e to the power 0.07 times n. Okay, sorry, you don't even need the times. From here, very clearly, e to the power 0.07 n will simply be a little rearrangement. You should get 25 over 3. Therefore, 0.07 n will be ln 25 over 3, implying n is equal to ln 25 over 3 divided by 0.07. this will give you 30.28. Alright. Now at this point, do take note. If it requires 30.28 years, that means that if you write the final answer as 30, it will not be enough, right? You can imagine it as a timeline, right? Let's say this is the years. And at 30.28, over here, we have 100,000 human beings. Right? So what happens if I round the answer to the nearest year? It will give me 30. And at 30, on this timeline, we have not reached the zigzag line yet. We have not reached 100,000 human beings. Which means that we're just wrong. In other words, you're going to have to disregard your standard rules of estimation and deliberately round upwards to 31, even if we have 30.2. I will deliberately round upwards to 31. And so the year will actually be 2051, not 2050. Now, there is some room for contention over here, which some people will argue about, which is that, but the math problem says the year in which the population hits 100,000. And if we substitute in 30.9, for example, you will see that we have already hit 100,000. In other words, this red color zigzag is inside this particular year, right? It's inside the year 30. So would it be wrong to say 2050 is the incorrect answer? So in order to do this kind of question, right, I'm going to be honest. This is no longer an issue of math. This is an issue of the formulation of the question itself. How well presented is the problem? How good is the English? I'm going to be honest here. If this happens in your national exams, go with your gut. In this problem, one advice I have for you, for example, is if you look at the first thing we circled, it says at the beginning of 2020. In other words, we have evidence to make the claim that measurements are done at the beginning of the year and not throughout the year. So if you argue 2051, you will probably be more correct than 2050. But if you ask me for my honest opinion, and I'm the teacher marking this examination, I will give the correct answer to both. Because the English does imply that 2050 is an acceptable answer. Because the zigzag line lies in the interval that depicts 2050. Again, it would be best if you could look to the question and see if there are any silent assumptions being made about the measurements that are taken. I don't recommend worrying too much about this because ultimately it will cost you a maximum of 1 mark, so it's not the end of the world. Right, so once we have this, the last problem asks for a graph of small letter n against capital P. There's just one big problem. The formula starts with capital P. In other words, we're going to have to do rearrangement ourselves. This is very similar to the investment fund question from earlier. We have P equals to 12,000 e to the power 0.07 n. Problem is, now we want n against P, we need n to be the subject. So let us start with the same steps as before. Right, I will make the exponential term by itself. I will then take the natural logarithm. Last but not least, I will move the 0.07 over. Like so. From here, then I can draw the graph. And let's see, we can expect something like that. Right? Oh, it won't be x, my mistake. It's gonna be p. Right, so it will be quite a straightforward logarithm graph actually. It's just a little scary because of the big numbers you see in the conversion. By the way, in the labeling of the graph, yet again, You can choose whether you want to use the original math problem or if you want to use the rearrangement. Either way is fine. Alright, so if you've made it this far, great job. It's been 2.5 hours. My lessons are normally 2 hours for those of you who don't know, right? For those of you who are overseas viewers. So this is definitely way longer than usual. I'm pretty sure university lectures tend to stick to 2 hours as well. So we are definitely going crazy today. Right, last problem will be short, so don't worry, we're almost done. First problem tells us to sketch LGX and LNX in the same diagram. So if you remember, for logarithms, a bigger base means you will be less dramatic, because logarithm is the opposite of exponential. So let's have a very dramatic person, y equals to ln x, and then a very sad person over here. That is such an ugly graph. Let me try again. And then a very sad person here, which will be LGX. Both of them conveniently will cut at x equals to 1. Right, so over here there really isn't too much for me to say. For part B, they ask us, sketch on the same axis the graph of ln negative x and 2y equal to x. Straight away we have a gigantic problem. Wait a minute, ln negative x? What does this mean? So for ln negative x, right, don't panic. If you think about it, it's just the same as ln x, except the person who gets eaten up has an extra minus sign slapped onto him. Only problem is you cannot do a logarithm of a negative number. So what we will do is we are going to throw in a negative number in the first place, so that negative x slaps a negative on the initial negative number. This will then produce a positive. In other words, all the x values going into the graph will be negative numbers. We will be looking at this side, not that side. So you can imagine for yourself, what happens when x equals to 1? Math error. What happens when x equals to 0? Math error. Wow, this sucks. What happens when x equals to negative 1? Right? Negative x. Then we will see that I have 2 ln positive 1, in other words 0. And therefore, negative 1 over here will be my x-intercept. From here, I think you can figure it out. If everything is negative numbers for the same result, that means that I should be increasing as I move towards the left. And therefore, I will get this floppy graph like this. Like so. Right? The asymptote, luckily, will still be there. You will realize, coincidentally, that this is actually a flip in the x direction. And why is that the case? Simple. If you remember compensation effect, we will need to undo the minus by adding a minus onto all the x numbers. And when you add a minus onto all the x numbers, all the positives will be flipped into becoming negatives. So this is actually compensation effect in effect, yet again. Alright, so once we have this sorted out, the next problem asks us to sketch the graph of 2y equal to x. Now 2y equal to x should be extremely trivial for you all. Let me use the highlighter. It will simply be like this. Right? Oh, pretend it passes through the origin. That was... You know what? I'll just redraw it. Fine. I'll just redraw it. Here. Pass through the darn origin. There we go. Here. This was for you. For the fans. Alright? So, here's our 2y equal to x. And now, they ask us, state the number of solutions to x equal to 2 ln x. Now, x equal to 2 ln negative x very clearly means that x over 2 equals to ln negative x. But over here, we said that 2y is equal to x. In other words, y equal to x over 2. Right? So in this case, we have y equal to x over 2 equal to negative ln x. So this will be the second graph, and that will be the first graph. In other words, it's literally the same math problem. So we will conclude one intersection, therefore one solution for the math problem. Simple. The drawing of the graph was not that simple though. Compensation effect. Please pay attention. Alright. So we are now in our final problem. And for the final problem, it is a little bit weirdly formulated. They simply tell you to draw two graphs, whichever ones you choose. And then afterwards, they want us to determine how many, or rather they want us to show with the picture of the two graphs that there's actually no solutions to the math problem at all. It is fake news, there's no solution. So what we will do is simply ask ourselves, what kind of reasonably easy graph can we draw from this? To work it out, I would like to invite you to try a surprisingly easy step. Let's just move the minus 2 over. In doing so, we have e power x minus 2 equals to lg x minus 3. And now I can just set y to be equal to these guys and we will have two different graphs. Now e power x minus 2 is simple, it's an exponential. I will move down 2 units. lg x minus 3 is a little weirder. I have the lg graph and then I will do compensation effect and move forward by 3. Undo the minus 3 by moving forward. Alright, so let us draw our graph. You can tell I'm very excited to end the class because the drawing is gigantic. Okay, so here's my 0. We're going to start with the easier one, e to the power of x minus 2. So over, oh, I just realized it's not even minus 2, it's plus 2. So it will actually be moving up, like so. Getting a little careless there, right? So the plus 2 means I'll be moving up. So before we begin even drawing the graph, do keep in mind the asymptote of the exponential, which is the x-axis, will also move up. So let us indicate that immediately. This will be y equals to 2. From here, then we can draw the exponential. Like so. Make sure to label the axial intercept at 3. So the y-intercept here is 3 because I can substitute in x equals to 0. As for the other person, log x minus 3. If you recall, the asymptote is here, the x-intercept is there, but everything gets moved forward by 3, by positive 3, due to compensation effect. So you can imagine for yourself, maybe 3 is somewhere here. I shouldn't write it there. Like this. Thereafterwards, the x-intercept will be at 4 because the 1 also gets moved forward by 3 steps. And from here, we can go on to draw the graph. Once the graph is drawn, I think you will realize, aha, one person is on top and going higher. The other person is below and starting to flatten out into a pancake. In other words, this guy and that guy, they're essentially turning away from each other. Even if you look backwards, they're turning away from each other. And therefore, they will never touch each other. So we will say that the graphs, or rather the loci, up to you, the graphs of y equals to e to the power of x plus 2 and y equals to lg x minus 3 have no intersections. And therefore, there must be no real roots, no solutions, at least among the real numbers. And we are done. QED. Right, so that is exactly what we wanted to show. So up to this point, that will be our final practice problem. Today was definitely a workout and then some more. 2 hours and 47 minutes almost, actually. So if you managed to go through this in one sitting, congratulations. Having said that, I don't recommend more than 3 hours straight of work generally for math. I feel like that's the limit because even in Singapore, the longest math papers are like exactly 3 hours. So I feel like that should be a good benchmark. So if you've made it this far in one sitting, again, congratulations. Even if you didn't make it this far in one sitting, if you made it this far, congratulations as well. This is a very crucial topic because we will be seeing logarithms in our linearization problems, and we will also be seeing logarithms when we move on to calculus, of course. So up to this point, if you have nothing else for me, I have nothing else for you. You are dismissed. Alright. Finally, we're done. I will actually be doing another stream later tonight in approximately maybe 3 hours. And we will move on to cover binomial theorem as a last little introduction to algebra that has powers in them. And once we are done with binomial theorem, then congratulations, we are done with this segment of the secondary 3 syllabus, and we will move on to coordinate geometry and geometric problems within the Cartesian coordinates. Alright? Yeah, you can look at this again. Once again, Merry Christmas, Happy Holidays, and yeah, hope you have a good time. I hope your Christmas, assuming it's belated, right? I hope your Christmas was spent on better things than whatever is on screen right now. Okay? Yep, I will be ending the stream shortly, and ladies and gentlemen, I will see you in the next video.